Alright, guys, welcome back. Today we're going to be discussing all of topic 5, which is thermochemistry, energetics, all that fun stuff. Um, a bit of preface. I find this topic is generally the hardest conceptually to wrap your head around, so if things don't make sense, I'm going to recommend, well, I always would recommend that you just rewatch the video a couple times, maybe read it in your textbook or find some other alternate explanation for it, but this topic particularly that applies. If you don't understand it the first time, try watching it maybe two more times, and if you still don't get it, read the read whatever textbook you're using or ask your teachers or whatever. It does take a while to click. Once it does click, though, this is a pretty simple. It's a lot easier once it clicks. Uh, and unfortunately, this topic is just probably one of the worst taught, in my opinion, because it's just clouded in a bunch of fucking. It's the mumbo jumbo. The terminology just it's too much to understand what it actually means. On a conceptual level. So that with that aside, with that aside, um, done. Let's get into it. So, energy is defined as the capacity to do work or produce heat. To put this in more, I suppose, terms you might understand, 1 joule of energy is how much energy it takes to accelerate a block that is 1 kilogram in weight, uh, 1 meter per second squared, over a distance of 1 meter. I don't know if that helps, but that's sort of what it measures it with respect to. So one. So how much? So let me say this again. How much the energy is 1 joule of energy is equivalent to having pushed a mass of 1 kilogram a distance of 1 meter, accelerating it at a meter per second squared. Yeah. Or 4.184 joules is the amount of energy required to raise the temperature of a gram of water by 1 degree Celsius. That's another probably more relevant way to, at least to chemistry. That's probably a more relevant way of putting it. Um, the next little bit here is the first law of thermodynamics. There's a bunch of them, but and you cover the second law and the third law in the higher levels. But the first law of thermodynamics basically states that it's a zero sum game. Energy cannot be created or destroyed. The amount of energy in the universe is constant. Um, you can convert energy from one form to another. Like you can go from gravitational potential energy to kinetic energy if you drop something, but the amount of gravitational potential energy and the amount of kinetic energy, the sum of those is always some constant. So there you go. There's many types of energy. However, we'll generally be focusing on chemical potential energy and uh, kinetic energy or heat, as we'll see it macroscopically. Um, Kinetic energy is the energy of motion, and if you have a group of particles, I should say, the temperature of that group of particles represents the average kinetic energy within that group. And heat, or Q, is a quantity of kinetic energy which is typically transferred as a result of a difference in temperature. It goes from high to low. So, and particles from warmer regions generally have, because they have more kinetic energy, they're moving faster. So they'll move into the colder regions, and on the way they will bump into other molecules. And since the collisions are elastic, meaning that uh, energy is conserved, well, I forgot if they're elastic or inelastic, but anyway, as a result of those molecular collisions, the fast molecule will slow down and the slow one will speed up until equilibrium is reached. Um, the conventions is that heat losses are given as negative and heat gains are given as positive. That's just convention. Um, so you'll generally always write minus Q lost equals Q gained, or another way that some people might prefer to write it is Q loss Q gain equals 0. The idea here is that it's the conservation of energy, and it would be the equivalent of saying GP. It would be analogous to saying PE gravitational potential energy plus Ke, kinetic energy, equals 0. It would be analogous to saying that. So let's go back and make sure I don't forget to put it. Don't make sure I'm not putting it on my whiteboard again. When I lecture, I have a bad habit of doing that. So yeah, we can use the formula Q equals mCp. Well, Q equals mc delta T to determine the amount of heat transferred within a body. So Q is the amount of energy lost or gained, M is the mass of the substance, delta T is the difference in temperature, and Cp is the specific heat capacity. That's just a constant. That's either given to you in your data booklet in the question, or you're probably going to be expected to memorize the C value for water, which is just 4.18. Yeah, and otherwise it should just be given to you. Different substances have different heat capacities. They're over a range. They're constant over a range of temperature for solids and liquids, but not gases. Those are the units, but it doesn't really matter. So here's a sample question. Calculate the heat flow associated with 150 grams of H2O, changing temperature from 80 to 23.5 degrees centigrade. So we plug it in, Q equals mc delta T, plug in your numbers. Temperature difference, remember it's always temperature final minus initial. So final minus initial. Note that difference in degrees temperature. The delta is in Kelvin is the same as the delta in Celsius. And there you go, it's minus 35.5 kilojoules. You'll more often see values quoted in kilojoules in chemistry just because chemical reactions tend to release a lot of heat. However, you should be mindful of what units you're working in, because some equations, particularly at the higher level, they are sensitive to what unit you plug in. Lastly, we know all this sort of theoretical stuff, but how do we actually do this in the lab? How do we do this sort of thing in the lab? And the way we do that is we sort of measure it using something called calorimetry, which is the measure of heat flow, and we use a calorimeter to measure the heat flow. It's basically just a closed system. You plug in a thermometer. You put in it's just a sealed container that you put a thermometer in. That's really all it is. And the idea here is that you know the mass of what you put in there. You'll know what the mass is you put in there. You presumably measure that out before. You presumably know the C value. You can probably just look that up in the back of a textbook or whatever. And you use the calorimeter to determine delta T, because you have a thermometer in there. You can take a final and an initial reading. However, keep in mind that these things aren't 100% efficient. Some heat will be lost to the walls, and by extension the surroundings. That's probably your most common error, just heat loss as a result. The materials you actually built the calorimeter on can really determine how big of a problem this will be. So in the case of this simple coffee cup calorimeter, the styrofoam actually has a fairly high heat capacity and therefore won't absorb much heat, whereas compared to this more sophisticated one that is made of aluminum, it looks like it's made of metal. Metals will tend to absorb a shit ton of heat, and that's a big source of error since that's a lot of heat loss. So yeah, and then here's another sample question. A piece of iron at 99.8 degrees centigrade was dropped into 175 degrees water with 21 degrees Celsius with a coffee cup calorimeter. Calculate the final temperature. So the thing the key to doing this problem is that the energy lost by the iron, so the heat energy lost by the iron, had to be gained by the water. And once you do that, it's fairly straightforward. You just put a minus sign there because that's convention, I guess. And then you plug and chug in your numbers, and you get 24.8 degrees centigrade. Yeah. Yeah, that's all there is to it. Thank you very much.